Hello all, this is Dr. A. Anuja, Assistant Professor, Department of Mathematics, Arulmigu Palani Andavar Arts College for Women, Palani. In this lecture, we are going to see about introduction of inner product space. So in this topic, we are discussing in the three-dimensional vector space. What is vector space? It should be satisfy these three conditions. It is possible to talk about the length of the vector and angle between two vectors. These concepts, the angle and the length are defined in terms of dot product and scalar product. So length is using in a dot product and angle is using in a scalar product of the two vectors. And dot product of u is equal to a1, b1, c1 and v is equal to a2, b2, c2, which is defined by u dot v is equal to a1 into a2 plus b1 into b2 plus c1 into c2. The length of u is given by root of u dot u and angle theta between u and v is determined by cos theta. It's nothing but u dot v divided by root of u dot u and root of v dot v. Hence, u and v are perpendicular or orthogonal if and only if u into u dot v is equal to 0. Suppose u and v are perpendicular means obviously u dot v is equal to 0. U dot v is equal to 0 means those vectors u and v are perpendicular or orthogonal. And the next, a inner product on a vector space is generalization of the dot product, and in terms of such an inner product we can define the length of the vector and angle between two vectors. And the study will take some restriction to the concept of perpendicularity of two vectors. And now we are going to see about the definitions and the examples for the inner product space. And the definition, let V be a vector space over F. An inner product on V is a function which assigning to each ordered pair of vectors u, v in a V. A scalar in a field F, it's denoted by u, v, satisfying the following conditions. So the conditions are, the first one, the inner product of u plus v, w is equal to inner product of u, w plus inner product of v, w. And the second one, the inner product of alpha u, v equal to alpha into inner product of u, v. And the third condition, the inner product of u, v equal to inner product of v, u conjugate, and where the inner product of v, u bar, it's a complex conjugate of inner product u, v. And the fourth one, inner product of u, u, it's greater than or equal to 0, and the inner product u, u equal to 0 if and only if u equal to 0. These four conditions for the inner product. If one vector space has satisfied these four conditions, we can say that the space is an inner product space, and all the vectors u, v, w are all belongs to in the vector space V, and the scalars alpha, beta, these are belongs to in the field F. Every vector space with an inner product space, inner product defined on, it's called the inner product space. A inner product space is called a Euclidean space or unitary space according to as the field or real numbers or complex numbers. And the note, if F is the field of real numbers, then the conditions 3, which means the conjugate conditions form u, inner product of u, v equal to inner product of v, u when field has a real numbers. And further, and the third condition asserts that inner product of u, u is always real, and the fourth condition is meaningful whether field is real or complex number. And in note 2, if we take the inner product of u, alpha, v, first we take the alpha. The alpha, the scalar is in the second one. So if we take it in an outside, obviously it will be convert into the conjugate. So alpha bar of inner product of u, v. So the inner product of u comma alpha v equal to taking the whole bar inner product of alpha v comma u conjugate. And the next we'll take the alpha bar scalar is an outside, and alpha inner product of v comma u whole conjugate, and alpha bar and inner product of v comma u bar, and this nothing but alpha bar of inner product of u comma v. And the third one, inner product of u comma v plus w is equal to inner product of u comma v plus inner product of u comma w. So first we take the conjugation and we are splitting the terms using the additions, and again we take conjugate and we replacing right as an inner product of u comma v plus inner product of u comma w. And the fourth one, inner product of u comma 0 equal to, in this case v is equal to 0, and the next one u is equal to 0 means inner product of u comma v equal to 0. First we consider inner product of u comma 0 equal to, if we multiple with 0 then only the v is converted to 0. So that's why we taking inner product of u comma 0 into 0 equal to, take 0 as an outside, so 0 into inner product of u comma 0, anything is multiple with 0 will get 0. And similarly we can apply for the case inner product of 0 comma v equal to 0. And now we are going to see about one theorem. The statement of the theorem, the norm defined. So they are giving the 4 subdivisions. We have to prove this. So the norm defined in inner product space V has the following properties. The first one, norm of x is greater than or equal to 0, and norm x is equal to 0 if and only if x is equal to 0. And the second one, norm of alpha x is equal to, in the scalar it will take a modulus and mod of alpha and norm of x. And the next third one is quartz inequality, which means modulus of inner product of x comma y, it's less than or equal to norm of x, norm of y. And the fourth one, triangle inequality, and norm of x plus y is less than or equal to norm x plus norm y. The first one, norm x, so we can written in the norm x as an root of inner product of x comma x, it's by the definition of unit norm. The root of inner product f comma x, it's greater than or equal to 0, and norm x is equal to 0 if and only if x is equal to 0. Hence proved the first one. And the second one, norm of alpha x squared is equal to, so first we are writing in the norm in the form of inner product. So inner product of alpha x comma alpha x, and take alpha in outside for the first term. So in second term only we have to take a conjugate. The first term there is no need to take a conjugate, by the definitions already we seen about the notes. And alpha of inner product of x comma alpha x, and the second term will take the scalar as an outside, it will convert into the conjugate of alpha into alpha bar inner product of x comma x, and the alpha into alpha bar, it's nothing but modulus of alpha squared, and inner product of x comma x is a norm of x squared. So therefore we are cancelling the squares on both sides, we'll get norm of alpha x is equal to modulus of alpha into norm x. And the third one, the inequality is trivial true when x is equal to 0 or y is equal to 0. So we'll assume x is not equal to 0 and y is not equal to 0. We'll consider the another vector z is equal to y minus inner product of y comma x divided by norm x squared into x. So then the inner product z comma z, it's less than or equal to 0. So we are applying z values into the inner product z comma z. So it becomes inner product of y minus inner product of y comma x divided by norm x squared into x comma y minus inner product of y comma x divided by norm x squared into x. In this case we will multiple with the first we are considering the first term and compare with the second terms. So first we'll take y and y to y and y to that second term, inner product of y comma x divided by norm x squared into x. And another day, the second term, inner product of y comma x divided by norm x squared multiple with y, and the y comma x norm x squared into another term. So it becomes inner product of y comma y minus inner product of y comma x conjugate, because we are multiple with the second one. So if we take this is a scalar, means it will take a conjugate. So that's why y comma x bar divided by norm x squared into y comma x, and minus y comma x divided by norm x squared x comma y, and again will multiple second terms, means the one term has a conjugate. And the next we are expanding this, y inner product of y comma y is written as a norm y squared minus inner product of y comma x bar, inner product of y comma x divided by norm x squared minus inner product of y comma x, inner product of x comma y divided by norm x squared plus inner product of y comma x into inner product of y comma x bar divided by norm x squared. So we are cancelling these second term and fourth term, because both are have a different signs. So finally we'll get norm y squared minus inner product of x comma y bar and inner product of x comma y divided by norm x squared. So we'll take LCMs and take it in on the left side. So therefore 0 is less than or equal to norm x squared norm y squared minus modulus of inner product of x comma y squared. So minus norm modulus values, take it in left side. The equation becomes, the inequality becomes modulus of inner product of x comma y is less than or equal to norm x norm y. This is the squash inequality. And the fourth one, triangle inequality. So modulus of x plus y, norm of x plus y squared is equal to inner product of x plus y comma x plus y. So previously we did this comparing these two terms on multiple, we'll get it. So it becomes inner product of x comma x plus inner product of x comma y plus inner product of y comma x plus inner product of y comma y. By the definitions from the inner product space, it becomes norm of x squared plus inner product of x comma y plus inner product of x comma y bar plus norm y squared. And from the complex theory we'll get 2 of real inner product of x comma y, and the equation becomes inequality less than or equal to norm x squared plus 2 modulus of inner product of x comma y plus norm y squared. So we are applying third result, will get less than or equal to norm x squared plus 2, because in third we prove modulus of inner product of x comma y is less than or equal to norm x norm y. We are substituting in the middle term, so we'll get less than or equal to norm x squared plus 2 into norm x norm y plus norm y squared. So the triangular inequality is therefore model norm of x plus y squared is less than or equal to norm x squared plus norm y squared. We are cancelling square on both sides. We'll get therefore norm of x plus y, it's less than or equal to norm x plus norm y. This is nothing but triangular inequality. Hence proved the theorem. Thank you.